In this tutorial, we're going to talk about deriving the other two Maxwell laws in differential form. These will be curl laws. Let's start off by considering a point in space, just to get us oriented. We've got a point in space up here, and where is it located? Let's be clear about that. There's an origin of our coordinate system, and there's some vector that locates this point in space, and we're going to call that vector, as we always do in this class, vector r. And at that location, we can of course consider that there is some electric field, and it points in some direction, and we'll name that E, the electric field at that point in space, and we could also pay attention to it having a location in time. Now, we want to learn something about the electric field in that location. What do Maxwell's laws tell us? Well, Maxwell has a law that in the integral form says this. It says that the integral along some sort of closed path of electric field dotted into small path elements so that you create a complete path equals a surface integral of the negative time derivative of magnetic field dotted into the surface element d sigma that we saw in a previous derivation. So let's draw a path. So here is a possible path, some sort of object in space, some path. And we can define some path with a direction that we travel the path. So I'm going to call that path P, and that's a surface bounded by P. If path P lies in a plane, you could take the surface to be the area in that plane, but you could also blow a soap bubble out and make it a three-dimensional curved surface. And we can now define along this path at that location what that differential path length element is. That's just some little amount dl right there. So that just allows you to picture what E dot dl means. You have a path, you have an electric field, and it has a dot product along the direction of the path. You sum it all up. We have a name for that. This quantity here, the integrated E dot dl along an entire path, that's called the circulation of E along path P. And we can actually write out a statement about that. We can say that the circulation of E along path P, well, the total circulation, we can write it this way. We can say must be equal to a strange quantity which we'll call the circulation, I'll just write circ, per unit area of every part of this area here. If we just add up the circulation per unit area of E along everywhere along in that surface, this is the surface integral. By definition, if I add up the circulation per unit area of something over an area, I must get the total circulation. This has a graphical interpretation you've probably seen before. If I take two little bits of circulation at two little locations, you've probably seen that drawn as like two adjacent squares. Here's the path along which I'd measure the circulation centered to this point in space, and then the adjacent neighbor, I calculate the circulation here, and what you see is that those interfaces cancel, and so the summing up of the circulation per unit area at two different locations gives me a total path along the perimeter where those interior faces canceled out. So that's what you should be thinking about here, that the total circulation along a path is equal to circulation per unit area everywhere inside of that path, And that's because the circulation along each little element, what adds up when you add them all up is just the outer perimeter. Everything else cancels out. So we can continue to write what this is equal to. We can say circulation per unit area is a quantity that we're going to give a shorter name to. We're going to call that the curl of E. Still times d sigma, the area. And now mathematically, it turns out that the curl of E can be written using a del operator, as something you've seen in your math courses. The mathematical definition of curl is del cross E dot d sigma. Now we've got a situation where, as with the earlier Maxwell laws, we have, this quantity here, the circulation of E, is equal to this surface integral, but it's also equal to this surface integral. So if I just copy this guy out to here, I've got the integral of minus dB dt dot d sigma, leaving off the dependences on r and t for the moment, equals this surface integral. And so now I have two quantities that seem to be equal, this and this. So I can go ahead and set them equal to each other, and I get that the curl of E, and now I'll put back the explicit dependence on space and time, curl of the electric field, how much it curls, must in each point in space be equal to the negative time derivative of the magnetic field. This is what I call Maxwell's third equation. And again, what's nice about this is we've gone from an integral expression, which only tells us about what's summed up along some path in space, to what we started out with, where we're just considering one point in space right here. And now we have an equation for the electric field at that particular point in space. So it's a local equation for how its derivatives are related to some physical quantity on the right. Very similarly, we can write a similar approach for B. The Maxwell equation for the circulation of B along a path, writing it where there's a dependence on r and t there that I'm not bothering to write. The physical equation is that that's equal to a surface integral of the following quantity, fundamental constant mu naught, current density J at that location, plus a second term, which has to do with the electric field changing. Both of these are dotted into the surface area element. So this again is saying that the circulation of B is related to something physical, but we also know that the circulation of B, by this sort of identity here, the circulation of B is the area integral of the curl of B. And so setting these two equations equal, if they are independent of exactly what area you choose, so the integrands must be equal, this del cross B and this mu naught J, etc. So therefore, we now have an equation for the curl of B. Again, at any point in space, the curl of B is given by that integrand mu naught. So it depends upon the current density of that location in space, plus a second term, which is how rapidly the electric field is varying at that point in space. And this equation here I call Maxwell's fourth equation.